In the final lecture of this unit, we will look at solar system debris, meaning the remaining material that did not end up as part of the Sun or the major planets and moons. There are three main reservoirs for this material, meaning three major places where this debris is located. One is in the asteroid belt, between the orbits of Mars and Jupiter. The second is beyond Neptune, in that torus or donut-shaped area called the Kuiper Belt where Pluto lives. The final area is beyond the Kuiper Belt in a spherical cloud surrounding the entire solar system called the Oort cloud. This is where the long-period comets come from.
Typically, long-period comets are described as those whose orbits take longer than 200 years, while short-period comets take less time than that to orbit. A more meaningful distinction, though, is probably their place of origin. Short-period comets typically come from the Kuiper Belt, while long-period comets originate farther out in the Oort cloud.
The asteroid belt creates a border between the inner terrestrial planets and the outer gas giants. You can see that each of the planets follows a single curved path, but the asteroid belt takes up a much wider area over an AU wide. This belt is populated with over 1 million individual objects, each on average 1 million miles apart. These are rocky, airless worlds. Most are strangely shaped potatoes like the image on the left. Ceres, the largest asteroid, is pictured on the right and is large enough to be spherical. Though there are tens of thousands of asteroids, they don't add up to be very much. Ceres itself contains 1/3 the mass of the entire asteroid belt, and all the asteroids added together would still be smaller than the Moon.
Here you see a 2-scale image showing the sizes of the 5 largest asteroids as compared to the western United States. Dawn was a spacecraft that studied asteroids until 2018, and it traveled to Vesta first and studied it for several months before traveling to Ceres. Several asteroids also have symbols, but most do not.
The way the asteroids are often portrayed in movies is incorrect. Oftentimes, we see scenes where people flying spaceships are dodging around fields of rocky objects. In reality, though, the average distance between asteroids is 1 million miles. So if you were standing on one, the next one over would look just like a distant point of light. You wouldn't really be in any danger of hitting one. Studying asteroids is important for life here on Earth. Sometimes asteroids get knocked or kicked out of their orbits and end up on a path that takes them near the Earth. We can see evidence of some big craters, like Barringer Crater, sometimes just called Meteor Crater, in Arizona. This large crater was created when an approximately 50-meter or 160-foot wide object impacted the Earth about 50,000 years ago.
The objects entering Earth's atmosphere do not always hit the Earth, but can explode above the surface. In 1908, an incoming meteoroid exploded over Tunguska, Siberia, leveling a forest of trees, luckily in a relatively uninhabited area. More recently, though, in 2013, another similar object exploded over Chelyabinsk, also in Russia. In this event, over 1,500 people were injured, mostly from glass windows shattered by the shock wave of the explosion.
Another incoming asteroid impacted the Earth's surface, wiping out the dinosaurs 65 million years ago. I once had a professor who said that the reason why the dinosaurs are extinct is that they didn't have a space program. We can't control hurricanes, earthquakes, or volcanoes, but there are things we can do to mitigate damage from asteroids, so it's important that we pay attention to these hunks of rock floating through space. In the upper image, you can see the region in the Yucatan Peninsula of Mexico where this impact occurred. You can see an enhanced region in the lower image. The yellow circle around the edge is showing a ring of cenotes, or water-filled sinkholes that run along the border of the edge of the crater.
The impacting object actually shattered the bedrock where it hit, creating these sinkholes.
Just to clarify some vocabulary, a meteoroid is the name of the object that's flying through the sky, usually a piece of an asteroid. A meteor is the streak of light you see as the meteoroid is burning up as it enters the atmosphere. If the rock survives to impact the ground, those pieces are called meteorites.
So it flies through space as a meteoroid, appears as light as parts of it burn in Earth's atmosphere, and then if it hits the ground, it's a meteorite. Make sure you understand the difference between each of these terms.
Meteor showers are often caused by comets or asteroids that have broken up in space, and bits of them continue to burn up in the atmosphere when Earth passes through its debris stream. In class, we'll look at several meteorite samples. In the image on the left, you can see several streaks in the sky. These are images of meteors as their meteoroids burn up, burning as they enter the atmosphere. The image on the right shows the orbit of a meteoroid or a comet around the sun. The orbiting object will leave a trail of debris in its wake. In the area or areas where the object's orbit intersects the Earth's orbit, people on Earth will see meteors as Earth travels through that region, either once or twice a year, per year, depending on orbit. As I mentioned, it's important for us to be able to identify possible target objects that might impact the Earth. In 2008, a small object was detected flying toward the Earth. Scientists calculated its orbit and knew where it would impact the Earth. 19 hours later, several pieces were picked up in Africa. Luckily, this was a small object which mostly burned up in the atmosphere, and the 200-plus pieces that were recovered were quite small, not dangerous enough to hurt anyone. It does demonstrate, though, our need to be prepared. If a larger object comes along, we need to be able to do something about it so we're not part of the next mass extinction. And no, blowing it up wouldn't help, and it would probably make it worse. Here, you see a few more images related to this meteorite find. The observatory where it was found, the asteroid piece itself as it was flying through space, some of the burned up dust as it entered the atmosphere, and one meteorite sample.
In addition to NASA's Dawn spacecraft, other spacecraft have visited asteroids as well. The Hayabusa spacecraft were launched by the Japanese Space Agency. They were designed as sample return missions, where bits of the asteroid would be collected for later return to Earth. The sample collection equipment on Hayabusa 1 failed, so only a few grains of the asteroid were returned. Hayabusa 2 was more successful, and the sample is still being studied. NASA's OSIRIS-REx spacecraft is currently operating around asteroid Bennu. It will hopefully be returning a sample of an asteroid to Earth in the future as well.
And for those of you who won't be in class to hold the meteorite samples I have, here are a few images. Let's look at each one individually. Each of these different objects can give us a wealth of information about the solar nebula and how the solar system has changed over time.
We're going to look at 4 samples in this lecture, and you have an assignment that looks at 3 samples similar to some of those seen here. They aren't necessarily in the same order, though, so be sure to look at the images carefully.
This image is of an iron meteorite. Notice the display they built around it, as it was too heavy to move. Can you see the person crouched behind it to show the scale of this object? This would have come from a differentiated asteroid that was obliterated. This sample is a piece of that parent body's core. The rest of the asteroid probably no longer exists, as it's probably been smashed to tiny bits. This is another iron meteorite. In this one, those stripes you see are called a Wiedmann-Stauden pattern. Basically, this occurs when metal cools so very slowly that it actually crystallizes. The lighter gray and darker gray bits you see are 2 different minerals. There are lots of different kinds of meteorite samples we have that come from a huge number of different asteroid parent bodies. Many types are one of a kind. This image is of a chondrite meteorite. You see lots of round inclusions that come from molten droplets that solidified in a weightless environment in the early solar nebula. These samples retain the original chemical composition of the nebula from which the Sun formed, minus the hydrogen and helium and other volatile or unstable materials. This last one is a type of meteorite called a palisite, which is an achondrite, meaning simply not a chondrite. This type of meteorite is believed to have formed at the core mantle boundary of the parent asteroid. The small crystals are chunks of mantle material, specifically the mineral olivine suspended in metal from the core.
An impact must have blasted the parent body apart, and liquid metal from the outer core got splashed onto the crystals from the mantle, gluing them together.
In this image, you can see an illustration of the Kuiper Belt. The Sun and 4 planetary orbits you see are the outer planets. The inner planets cannot be seen on this scale. Beyond Neptune, billions of kilometers from the Sun, is a torus or donut-shaped disk of material where Pluto and other dwarf planets and many other small objects reside. It is similar to the asteroid belt, but it is far larger, 20 times as wide and perhaps 200 times as massive.
To date, we know very little about the Kuiper Belt, and only 2 KBOs have ever been visited by spacecraft.
Pluto is the most well-known of the Kuiper Belt objects. It was once classified with the other 8 major planets until it was demoted in 2006. It was then that the International Astronomical Union, IAU, formally defined the word planet. To be classified as a planet, an object must meet 3 criteria. The first is that the object must be in orbit around the Sun rather than a planet, and second, that it has to be of sufficient mass to be roughly spherical. Pluto meets these 2 criterion, but not the last one. To be a major planet, an object must have cleared the neighborhood around its orbit, meaning that it's gravitationally dominant in its orbit, without any other nearby objects other than its satellites that are affected by it. There are many other objects that share Pluto's orbit. Thus, it is classified as a dwarf planet. Here, Pluto is pictured with Charon, its largest moon. This table shows that Pluto is just one of many such objects. Pluto and Eris are of similar size, though Eris is much farther from the Sun. Haumea is about the same size and distance from the Sun as Pluto, but Mackay is smaller and much further away. Sedna is small and is much farther away from the Sun than any of the other objects listed here. Neither Sedna nor Quaoar are officially classified as dwarf planets yet, but they are both likely to be in the near future.
The New Horizons spacecraft was the first and only craft to visit a Kuiper Belt object. It was launched in 2006 and didn't arrive at Pluto until 2015. New Horizons was a flyby mission that flew past Pluto and its moons, photographing and studying the planet as it flew past at about 16 kilometers per second, or over 36,000 miles per hour. After passing Pluto, it made a course correction and flew past another KBO, now called Arrokoth, on New Year's Day of the year 2019.
Here are a couple of images taken by New Horizons. Pluto has a much more dynamic and geologically active surface than scientists predicted. There are glaciers of ices made not only of water, but ices of nitrogen, carbon monoxide, and methane. Pluto's surface is also host to mountains, cliffs, craters, and a polar cap of solid nitrogen. The zoomed-in area in the lower right photo shows the complex geology present on this small body. Pluto was discovered in 1930, while its largest moon, Charon, wasn't discovered until almost 50 years later. Pluto is now known to have 5 moons, and many other Kuiper Belt objects probably have their own satellites as well. Eris, Haumea, and Quaoar, and several other unnamed KBOs have been confirmed to have moons. Charon has what seems to be a strange orbit. Its orbit, though, is consistent with Pluto's rotational axis. Pluto, like Uranus, is so tilted that it looks like they roll rather than spin.
These two bodies are so close to one another that they circle each other in only about 6 days.
Pluto and Charon are also quite small. Together, they are smaller than the United States. Pluto is named for the Roman god of the underworld. His Greek counterpart is Hades. All Pluto's moons are related to Pluto and the underworld. Charon is the name of the boatman who ferries souls down the river Styx, which is another one of the moons. Nyx, a third moon, is named for Charon's mother. The final two moons are Hydra and Cerberus, the 9-headed serpent and 3-headed dog that guard the underworld. Pluto's symbol is a combination of the letter P and the letter L. These are not only the first two letters in Pluto's name, but also serve as a tribute to Percival Lowell, the astronomer whose observatory found Pluto in 1930.
After visiting Pluto, the New Horizons spacecraft moved farther out into the Kuiper Belt to visit Arrokoth, previously known as Kuiper Belt Object 2014 MU69. It had originally been nicknamed Ultima Thule, which means extreme limit of travel and discovery, so you will sometimes see that name on early images and graphics describing this discovery. You'll see it in this presentation as well, in titles and captions in a couple of the images on the next two slides. Here you can see several images of Arrokoth. The first image is when the spacecraft was still quite a ways off, but you could begin to see the shape. From the second and third images, you can see why it's important for us to send spacecraft to visit these objects. From far off, you don't get much detail. A smudge that looks like a bowling pin from far away looks more detailed and cratered close up. In the lower image, you can see Arrokoth and its reddish color. Notice also that it looks like a snowman or Star Wars droid BB-8 in shape. This sort of object is called a contact binary, meaning it's two separate objects in contact with one another. Before actually seeing Arrokoth, it was hypothesized that many Kuiper Belt objects might in fact be contact binaries. This was predicted based on the nebular theory and how we think all planetary and stellar objects form by accretion of materials. Here you see the process that probably occurred to make our space snowman. Each of these lobes had its own name. The larger one, called Ultima, and the smaller one, called Thule. So even though 2014 MU69 has the official name Arrokoth, it will still always carry the name Ultima Thule. Beyond the Kuiper Belt is a sphere of even more debris called the Oort cloud. The cloud is named for Jan Oort, the astronomer who first hypothesized about its existence. The cloud is believed to extend halfway out to the next star, where presumably the Oort cloud of that star begins. Much of what we believe is true of the Oort cloud is conjecture. The cloud itself is so distant and the objects within it so small that they are impossible to see. We know this material exists out there, though, as we periodically get cometary visitors from the Oort cloud in the inner solar system. This picture shows a series of scale images of our whole solar system to the inner Oort cloud. First, we see the inner solar system out to Jupiter, then out to the orbit of Pluto. In the third image, we see how far out dwarf planet Sedna is compared to Pluto. But then, see how far Sedna is compared to even just the inner border of the Oort cloud. Our solar system is really big.
Here is a characteristic image of a comet. As they approach the sun, comets have a bright nucleus surrounded by a fuzzy atmosphere with a long tail that trails it. Comets are classified in one of two groups, either long or short period. The comets themselves are not different, but they are grouped by their orbit and home location. Short period comets are those whose orbits bring them closer to the sun more frequently than every 200 years. These comets come from the Kuiper Belt. Long period comets come from the Oort cloud, and their orbits bring them into the solar system either on orbits that take longer than 200 years or they are one-time visitors that whip past the sun on their way out of the solar system, never to return. Comets are basically dirty snowballs flying through space. These dirty snowballs vary in size, but are typically a few miles across. When far away from the sun, they are frozen solid, but as their orbit brings them closer to the sun, they begin to melt. A fuzzy atmosphere called a coma begins to develop around the nucleus. In the upper photo, you can see a comet with two tails. Comets can have between 1 and 3 tails, one made of dust, one made of ions, and one made of sodium. In the lower picture, you can see a drawing of a comet's tail and how it always points away from the sun. The tail is sublimated or evaporated material that is carried away from the nucleus by the solar wind. The tail always points away from the sun, regardless of the direction in which the comet is traveling.
And the tails can be millions of kilometers long. After the comet rounds the sun and heads back into the outer solar system, the atmosphere freezes back onto the surface and the comet becomes inactive again and no longer has a tail.
Here's a close-up image of a coma. The coma of a comet can be huge, up to thousands of kilometers in diameter from a comet nucleus that is far smaller. Surrounding the coma is a cloud of hydrogen as well. The comet's nucleus is mostly ices of water and carbon dioxide and dirt. Carbon dioxide ice is often called dry ice. Comets also include other materials like ammonia and methane. Though this comet is illuminated and looks quite bright, that is only as a result of the sublimating ice. The surface of the comet itself is almost black from the dust left behind. Several spacecraft have visited comets. NASA's Deep Impact visited Comet Hartley 2 in 2010. This photo is an image of that comet. Prior to visiting Hartley 2, Deep Impact visited Comet Tempel 1 in 2005. It sent a projectile into the comet to study the material ejected by it.
Halley's Comet is probably the most well-known comet as it is a short-period comet, again meaning that its orbit brings it close to the sun more frequently than every 200 years. These short-period comets reside in the Kuiper Belt rather than in the Oort cloud. Comet Halley was the first comet to be identified as a periodic comet, meaning that the same comet was repeatedly visiting the solar system every 76 or so years. Halley has a very low albedo, or surface reflectivity. It is one of the darkest objects in the entire solar system. It is only visible to us on Earth when it's close enough to the sun to have a coma and a tail. Another mission called the Stardust actually collected a sample of a comet. Sample return missions are rare because they're very expensive.
The most recent completed cometary mission was the European Space Agency's Rosetta mission. Rosetta was an orbiter, but the mission also included a lander called the Philae. It was supposed to land on the comet and shoot harpoons into the surface to hold it down, as the comet's gravity would not be enough to hold it onto the surface. Unfortunately, the harpoons failed and the lander bounced across the surface of the comet. It sent back some data, but it died within days as its solar panels were not properly positioned due to its fall. The lower image shows a comet around which Rosetta orbited, Comet 67P Churyumov-Gerasimenko. It also looks a lot like a rubber ducky. Many comets look like this, as if they were two separate bodies that later struck together.
Finally, this last slide is just a vocabulary reference slide intended to hopefully clarify the difference between the types of solar system debris.